Control engineering is characterized not only by its precision in assembling complex physical systems, but also by its capacity for simplification. Although pH control plants are one of the most common systems in the industry, they are also one of the most complex to control due to the high rate of nonlinearity. Hi, I'm Axel, and in the present work we will apply the gain scheduling technique used for nonlinear system. We will design a PID controller that allows us to work in any range. By controlling a Festo prototype, which with its variety of interconnect devices, we will get to obtain this particular model. But before everything, what is gain scheduling? It is known that nonlinearity of a system occurs when the system output does not respond in the same way to inputs of equal size, making it difficult to design a PID controller. Gain scheduling proposed that in the linear zones we should not work in a single one, but as a set, and each one of them with different parameters to control it. That is why we will divide in 5 zones that, depending on which is our input step, our system will place us in one of them.
Our model consists of several elements. The one we will use are the acid tank, the base tank, and MISIC tank, the steering motor, the reflex pump, the drain valve, and the pressure sensor that is below the tank. These two pumps, the acid pump and the base pump, will transport the sulfuric acid and the caustic soda inside the liquid tank. These two pumps can be controlled with digital signal.
All these components can be controlled and read by LabVIEW, a software that makes it possible to create graphic design with various instructions, which can be controlled with a front panel. Finally, we use the EZ port, which allows us a bidirectional transmission of signal between the LabVIEW and Festo module. This is easy connect on the computer via EZ port server with graphical interface.
For the input signal, we will control the pulse width of the digital output. In this way, we will have a high or low float in the base point, while the acid point will always be constant. And all output signal, which will be read by the pH sensor, which was previously calibrated, will send the data in bits of the Arduino Nano that convert in data voltage and then in pH.
In LabVIEW, we will program the drain valve with a knob of control for a constant flow for 2 liters. For the active stirrer and pump, it will be the same control, but intended to be activated when it detects a level of 0.2 liters. Through MATLAB, we place the equation of the reaction between caustic soda and sulfuric acid. As can be seen, for each step input of equal amplitude responds differently. Now, using the Sigurd-Nichols open-loop tuning method, we will obtain the PID constants. At the time to take measurement, our graphic presents an abnormal signal too large to be a noise. For this reason, we are looking for other devices that could detect it. Finally, we found that there was a dielectric failure in the same Festo. As you can see, when I disconnect the Festo, the signal stabilizes.
It is important to calibrate the measuring instrument on understanding the behavior of the measured signal. This allows to estimate the integrity of the instrument and the reliability of the measurement.
Although the graph shows values that seem to oscillate in one value and have a linear behavior, this is not the case because the pH changes abruptly with any variation in the fluid.